So in the previous lesson, an assumption that we had made is that the redox reactions that we were studying, that we were looking at with the voltaic cell, were spontaneous. And the question comes up, well, what makes a reaction spontaneous? How do I know if it's spontaneous? And one of the things we've already looked at is the Gibbs free energy. And if that value is negative, then we know that a reaction is spontaneous. Well, there is another way of determining if a reaction is spontaneous, and that is your cell potential. Now, if your cell potential is positive, then the reaction is going to be spontaneous. And so this brings up a question that an assumption that we had made previously when we were looking at different types of reactions. Specifically, nickel, we know that in a single replacement reaction, nickel replaces silver. But we know that the reverse is not true. And we know that by using the activity series and remembering that in order for an element to kick out another element, it has to be higher on the activity series. Well, let's understand why now. Finally, we can understand why that's the case and not just make the assumption based on the activity series. Well, if I'm going to write out the reaction for nickel replacing silver, nickel will just be an atom and silver will be an ion. So it'll be nickel plus silver ion, and then that'll produce the nickel ion plus silver because nickel is now part of an ionic compound, and then silver is kicked out. And so what we need to do is we need to separate these reactions based on which one's oxidation and which one is reduction. So nickel is going to be oxidized, as you can see here, and I added the 2 electrons that have been removed from nickel, and then silver is going to be reduced. Now I can actually calculate the cell potential for this reaction by looking up the reduction potential of nickel. And remember, since this is an oxidation reaction, I'm actually going to flip that value, so I'm going to just make it a negative. So when I look it up, I get negative 0.28 volts for the reduction potential of nickel, and so the oxidation will be positive 0.28 volts. And then I look up the reduction potential for silver, and I get positive 0.80 volts. And so when I add them together to get my cell potential, I get positive 1.08 volts. And so because this value is positive, that means this reaction is spontaneous, and therefore you don't have to have any sort of outside input in order for that reaction to occur. So that's why nickel can kick silver out in a single replacement reaction. If you look at silver trying to kick nickel out, however, this is the reaction. I write out the reduction reaction for nickel and the oxidation reaction for silver, and then I find the reduction potential of nickel, which is going to be negative 0.28 volts, and then for silver I simply need to flip the reduction potential to get the oxidation potential. And so when I add these together, I get negative 1.08 volts, which means that this reaction is not spontaneous, and that is why silver cannot kick out nickel in a single replacement reaction. So now finally we understand the chemistry behind it. Well, all of that is great, but let's actually relate the cell potential, E, to your change in Gibbs free energy, because that is actually what helps us to understand whether or not a reaction is spontaneous. And so this is an equation from your reference table that will be given to you, and it's that delta G, which is your change in Gibbs free energy, equals the negative N. Well, N is your number of moles of electrons, okay, times Faraday's constant, which will also be given to you. Notice the units are coulombs, which is charge per mole, times your cell potential, or your electromotive force. So let's actually look at an example problem to understand how we can relate your cell potential to Gibbs free energy. And so in this reaction, what I first have to do in order to calculate the cell potential is I have to break these down into oxidation and reduction reactions. Well, here I've got bromine, and bromine, this is going to be an oxidation reaction, okay? And so with fluorine, that's going to be the reduction reaction, all right? And so I calculate the oxidation cell potential, and that's going to be negative 1.06 volts, and I get that value from my textbook, and I also know that I actually get the reduction potential from my textbook, and I just take the negative of that. And then I'm going to do the same thing, but for F2, it's going to be the reduction potential, which is plus 2.87 volts. And so when I add these together, I find that my cell potential is positive 1.81 volts. So now I'm going to plug this into my formula. I don't know my delta G, that's what I'm solving for. I know that my number of moles of electrons is 2, because I've got 2 electrons for each of these. 2 are going to be removed, 2 are going to be accepted. So 2 electrons. Okay. I know my Faraday's constant, because that's given to me. And then I know my cell potential now, which is positive 1.81 volts. So I can plug this in. Notice unit-wise, the 2 moles of electrons don't have units. I have coulombs per mole for Faraday's constant. I've got joules per coulomb for my cell potential, because remember, volts, the units for volts are joules per coulomb. And so when I cancel everything out, I'm going to end up with joules per mole, which are my units for my change in Gibbs free energy. And so what I get is negative 349,000 joules per mole, or I could just say negative 349 kilojoules per mole. Notice this value is negative. My cell potential is positive, which makes sense because this is a spontaneous reaction.